Hello, Professor Tel and committee members, Professors Gabriela, Anderson, and Bruno. My name is Aloisio Dourado. Thank you for participating in the evaluation of my work towards complete 3D indoor scene understanding from a single point of view. This is the presentation outline. It follows the structure of the thesis: introduction, background, and previous works. Chapters 4 to 8 relates to the stages of our work. We conclude in Chapter 9. Human visual perception is the ability to infer information from the environment through our binocular vision system. We can naturally perform tasks such as scene classification, am I in a church, hospital, or school? Depth estimation, which object is closest to me, can I reach it? And object identification, detection, and localization. Is this object near me a fork or a spoon? This ability of reasoning about 3D scenes is considered to be one of the fundamental problems in computer vision. Despite the progress that has been achieved in the past few decades, general purpose scene understanding is still a very challenging task. Automatic understanding of the complete 3D geometry of a scene has many applications, such as robotics, surveillance, assistive computing, and self-driving cars. Augmented reality and immersive spatial audio reproduction are other examples of applications. We focus on semantic scene completion because it is one of the most complete tasks related to indoor scene reasoning. The task aims to infer semantic labels to all the field of view, including surface and inner voxels in the visible and occluded spaces. Problem statement. Despite the advances observed in the past few years, there is still room for improvement. Although some algorithms may be used in some applications as they are, the state-of-the-art models available by the time we start our research were still far from ideal. We identify 4 main deficiencies in the approaches available by the time we started our research. The RGB part and other modes of the RGBD images are not completely explored by available solutions. Some techniques widely used in 2D deep CNN training, like one-cycle learning and data augmentation, have been neglected in most SSC works. None of previous works have explored the use of unlabeled data to improve generalization power of the models by domain adaptation and semi-supervised training. And current solutions are limited to the restricted field of view of depth sensors like Kinect, for example. The general objective of this research is to propose, implement, and evaluate new solutions and models that could push SSC solutions towards a complete understanding of the whole indoor scene, including enhancing the coverage and quality of the inferences. We arrange the specific objectives in the 3 stages of our research. We started with the semantic segmentation in 2D due to the abundance of works and less resource requirements. In 3D domain, our objectives were to apply current trends on 2D deep CNN training protocols to 3D semantic scene completion networks, to propose and evaluate a new semantic scene completion model that uses the RGB information present in RGBD images and overcome the sparsity problem when projecting features from 2D to 3D, to propose and evaluate a multimodal deep neural network to explore multiple modes of the RGBD images and enhance 3D SSC scores, and to propose and evaluate the benefits of the use of unlabeled data in 3D semantic scene completion through semi-supervised learning. In the 360-degree scenario, the objective was to propose and evaluate a solution to perform panoramic semantic scene completion using existing regular RGBD datasets for training. We were glad to have published results of each one of the stages of our research. Chapter 2: Background and Related Concepts. Computer vision is the main research field of this thesis. We are particularly interested in stereoscopic vision. We start our background chapter by showing how stereo computer vision relates to the human vision system. In stereo vision, the set of geometric relations between the 3D world points and their projections onto the 2D image is known as epipolar geometry. In this section, we briefly introduce the epipolar geometry following the notation and definitions of Hartley and Zisserman. Image and scene reasoning evolution. In this section, we present some background related to the evolution of computer vision since the early approaches until current stage of development, achieved with the use of deep convolutional neural network for image classification and image segmentation. In the last section, we presented how convolution-based networks evolved and achieved impressive results in 2D tasks. In this section, we present some background related to 3D representation for using with 3D CNN. A voxel volume is a regular grid in three-dimensional space. Each position of the 3D grids represents a voxel. In a voxel volume that represents the visible part of a scene, each voxel stores a binary information indicating whether or not the voxel belongs to the visible surface. In our text, we provide the expressions used for lifting from the depth maps to voxels. The voxel grid obtained from a depth map is a very sparse representation of the scene, as can be seen in the figure. Only a few voxels contain useful information, while all other voxels value 0. Besides that, there is no differentiation between visible and occluded regions. Although this representation can be used as input to a 3D CNN, the convergence of the network may take too long to obtain or even may not be obtained. The truncated signed distance function coding procedure is a very common procedure to tackle the sparsity problem of volumetric representations. In TSDF encoding, every voxel stores the distance to its closest surface, clipped in a given range, normalized to -1 to 1, as illustrated in the figure. As deep neural networks require high amounts of labeled data to be trained, transfer learning and semi-supervised learning methods can be employed to reduce the cost of acquiring training data. In the text, we provide a brief introduction to transfer learning and domain adaptation. The figure shows an example of transfer learning application. Chapter 3. Related works. In this chapter, we present some previous works closely related to our research project. Here, we focus on depth-enabled inputs for scene understanding like RGBD sensors, binocular images, and scene scan systems from a single point of view. We present works on 2D RGBD semantic segmentation, partial 3D scene reasoning from RGBD, and 360-degree scene understanding. However, we give a special attention to 3D semantic scene completion, which is the focus of our work. The term semantic scene completion was introduced by a group of researchers from Princeton University. The task aims to jointly infer the occupation of the occluded part of the scene and the semantic labels for all the voxels in the field of view. The figure illustrates the expected output of the task. This is the seminal paper of semantic scene completion. Their network is called SSCNet. With SSCNet, they proposed several concepts and ideas that are still used nowadays. The first contribution was the use of 3D dilated convolutions to enhance receptive field. The term receptive field represents the relationship between the feature of a given layer and the area of the input image that influences that features. To learn the relations between objects in the scene, it is necessary to keep a big enough receptive field in the deeper layers of the network. The usual way to achieve a larger receptive field is to enlarge the filters of the convolutions. However, it would consume too much memory, especially in 3D. To solve this problem, Song's team extended the dilated convolution to 3D. Another important contribution was the flipped TSDF encoding. Using regular TSDF encoding, the transition from the visible region to the occluded region is very smooth. Unlike TSDF, FTSDF provides a stronger signal in the surface. In FTSDF, the transition from the visible region to the occluded region goes from 1 to -1, providing a high gradient and thus a stronger signal in the surface. At last but not least, they also introduced SunCG, a large dataset of synthetic indoor scenes used to pre-train SSC neural networks before fine-tuning them to a real datasets like NIU DV2. The use of this fine-tuning strategy improves the generalization and reduces overfitting. Prior to our first work on semantic scene completion, there were some papers that explored the ideas introduced by SSCNet. We classify these works in three groups. The first group is the depth maps only approach. SSCNet itself is an example. After SSCNet, some other works achieved better results with more efficient training pipeline and improved network architectures. The next group is depth map plus RGBD. Color information is expected to be useful to distinguish objects that approximately share the same plane in 3D space, and thus are hard to be distinguished using only depth. The third group is depth plus 2D segmentation. Models in this category use a two-step training protocol, where a 2D segmentation CNN is first trained, and then it is used to generate input to a 3D semantic scene completion CNN. After semantic scene completion, which results are restricted to the limited field of view of the regular RGBD sensor, we present some works using 360-degree sources for other 3D tasks. In Chapter 8, we present an approach to use this kind of source to achieve 360-degree semantic scene completion. We conclude Chapter 3 presenting the datasets used in our experiments, NYU DV2, NYU CAD, and SunCG. From now on, we will start to address our own contributions. The goal of Chapter 4 is to confirm the effectiveness of fully convolutional network approaches for semantic segmentation in comparison to more traditional approaches. We also want to access the benefits of domain adaptation techniques applied to deep learning models. We choose to start our work in the 2D domain because 3D tasks are much more complex and require much more computational power. This way, we start to explore domain adaptation and segmentation in an easier domain. We choose to investigate the human skin detection problem as a study case because it is binary, simplifying the analysis, and it is a widely studied topic of computer vision. Besides that, it is a research field where some criticisms regarding the use of CNNs and FCNs are made, like the need for large training datasets, the specificity or lack of generalization of neural nets, and long prediction time. Our objective was to refute those criticisms. We performed in-domain and cross-domain experiments. The goal of in-domain experiments was to compare local CNN to holistic FCN and also compare to current color-based state-of-the-art. The goal of cross-domain experiments was to access the gains of three simple domain adaptation methods. We used 4 datasets in our experiments: SFA, Prathypan, Compact, and VPU. We trained 2 models, one local patch-based CNN and a holistic U-shaped FCN. We also tested 3 domain adaptation approaches: inductive transfer learning by fine-tuning parameters of a model to a new domain, semi-supervised and unsupervised domain adaptation by cross-domain pseudo-labeling, and a combined transfer learning and domain adaptation approach. Here you are some qualitative results comparing the domain adaptation methods using no real labels from target. The combined approach presented better results. Here we compared regular supervised training to the combined domain adaptation approach, varying the amount of real labels from the target. The combined DA systematically surpassed regular supervised training. Chapter Summary. We refuted the criticisms regarding the use of deep convolutional networks for skin segmentation. Our 2 CNN approaches performed much better than the color-based state-of-the-art. Our holistic UNet inference time was enough for real-time applications. With no label data, our semi-supervised approach presented a 60% improvement over the color-based state-of-the-art. The work presented in this chapter was published in the 2021 CBGRAPH Conference on Graphics, Patterns and Images. Chapter 5. Using RGB edges to improve semantic scene completion from RGBD images. Prior to the beginning of our research, most works on SSC used either depth only or depth with color through projecting 2D segmentation features to 3D. One of the challenges of color-enabled approaches was how to efficiently encode colors or 2D features to 3D. In this chapter, we present a novel strategy to efficiently encode information from RGB to 3D. Our approach is called EdgeNet. It consists of extracting the edges of the RGB data and projecting to 3D using depth information. As the projected data is binary, we can easily apply FTSDF to it, solving the encoding problem. Our implementation is extremely efficient. We use offline FTSDF calculation using portable C++ CUDA code. We provide a software interface between CUDA and Python, which makes it easy to be used by other solutions. Processing code is independent from the deep learning framework, which gives freedom to choose and also consumes less resources during training. Our network follows an U-shaped design with dilated ResNet models. We evaluated 3 fusion schemes: early fusion, mid fusion, and late fusion. Our approach presented better training time and better results comparing to SSCNet. We achieved a new state-of-the-art result of SunCG. All new aspects of our solution contributed to the improvement. Middle fusion and late fusion schemes presented similar results. Qualitatively, our results were also better. Here, we see a better classification of a given object. Here, we see that we are able to classify plain objects hanging on the wall, which are invisible to SSCNet. And here, we see an annotation error in the ground truth that SSCNet wasn't able to get. The contributions of this chapter were a new end-to-end network architecture, a new RGB encoding strategy, visually perceptible improvements in 3D, improvement over the state-of-the-art results on SunCG. We surpassed other end-to-end approaches on NYU v2, and an efficient and lightweight training pipeline for the task. The work presented in this chapter was published in the 2020 International Conference on Pattern Recognition. Chapter 6. Multimodal 3D semantic scene completion with 2D segmentation priors and data augmentation. In Chapter 6, we continue to evolve the SSC task, introducing a multimodal solution and an efficient way to exploit 2D segmentation priors. One of the main challenges of depth map plus 2D segmentation approaches is how to fully use the output of the 2D network given the memory constraints. Previous solutions uses either encoding techniques that reduces the amount of semantic information or uses internal features of the network that are not completely semantically rich. Our approach consists of using a full resolution FTSDF encoded surface volume alongside a semantically rich bimodal 2D network output in the form of 2D priors projected to 3D, but in a lower resolution. This way, we preserve the semantics from the 2D segmentation network without consuming too much memory. The loss of fine details is compensated by using a high-resolution FTS surface volume input in the upper branch. The use of 2D predicted probabilities instead of inner segmentation features was the first hypothesis that we tested in this chapter. The second hypothesis related to the use of 3D data augmentation to reduce overfitting and reach better results. We also introduced a lightweight DDR block with fewer batch normalization layers to keep memory profile low. Data augmentation, which is widely used in 2D applications, has not yet been used in 3D's SSC. In this chapter, we introduced the use of data augmentation applied directly to the projected 3D volumes of the SSC solutions. Our approach consists of 3 simple and fast 3D transformations. The transformations are random x-axis flipping, random z-axis flipping, and random x and z axis swapping. All transformations are randomly applied during training. The use of this strategy during training is equivalent to augment 8 times the size of the dataset. All operations are done in the GPU tensors and can be easily executed in parallel with almost no impact on training time. This strategy also enables test time data augmentation. This chapter also includes a comprehensive ablation study. Each one of the aspects of our solutions contributes to enhance the results. Our experiments also includes an oracle test to estimate how far the model would go if the 2D segmentation was perfect. We compared our results to the state-of-the-art on SunCG, NYU DV2, and NYU CAD. Overall, our results were better than previous works. The qualitative analysis shows that our results are much better than the baseline model. To conclude, we present the contributions of the chapter. Spawn, a novel 3D SSC network that explicitly fuses semantic priors with high-resolution structural information from depth maps. BNDDR, a line-to-8 batch-normalized DDR module with higher discrimination power than its predecessors. 3D data augmentation, a mod and resolution-agnostic strategy that may be applied to other SSC solutions to reduce overfitting. Besides that, our solution surpassed all the previous solutions, including the ones with higher computational complexity. The work presented in this chapter was published in the 2022 Winter Conference on Applications of Computer Vision. Chapter 7, Exploiting Unlabeled Data to Enhance SSC Scores. A crucial difficulty in semantic scene completion is the lack of fully labeled real-world 3D datasets, large enough to train the current data-hungry deep 3D convolutional networks. In this chapter, we access the benefits of semi-supervised learning by exploiting unlabeled data from real datasets. Our solution is a semi-supervised training approach that we call S3P, semi-supervision via segmentation priors. In our experiments, we used Spawn, our state-of-the-art architecture, as a base model. S3P was partially inspired by the pseudo-label method. However, there are important differences. The original pseudo-label method trains the network in a supervised manner, using labeled and unlabeled mini-batches simultaneously. The same model is used to generate predictions and pseudo-ground truth for unlabeled data. The quality of generated pseudo-labels starts low, but improves as the training iterates. Instead, in our S3P, we feed the network with unlabeled data from real dataset and use a pre-trained 2D network to generate high-quality 2D prior probabilities for that data. Then, we project the 2D priors to 3D and argmax it to generate 3D ground truth that will be used by the semi-supervised loss. During training, both labeled and unlabeled data are used. We provide a training algorithm in the thesis document. The training algorithm controls the amount of unlabeled data used and the weight of the semi-supervised loss via 2 hyperparameters. As the generated ground truth only provides information for the visible surface, the semi-supervised loss only evaluates the visible voxels. The benefits of S3P semi-supervision are impressive. S3P pushed the Spawn results to a new state-of-the-art level. Qualitative results on NYU CAD are remarkable. It is very hard to know differences between Spawn plus S3P and the ground truth. To conclude this chapter, we would like to highlight the remarkable results of S3P. Spawn alone had consistently surpassed the previous state-of-the-art. However, when combined to S3P, presented unprecedented scores, achieving a boost higher than 12% on NYU DV2. Chapter 8, Extending Semantic Scene Completion for 360-degree coverage. Previous works on SSC only perform occupance prediction of small regions of the room covered by the field of view of regular RGBD sensors in use. One key aspect that favors limited angle approaches based on single shot from regular RGBD sensors is the abundance and variety of available datasets with densely annotated ground truth, which enables the training of deep CNNs. On the other hand, by the time we wrote this chapter, there were no fully annotated 360-degree panoramic datasets to train a 360-degree SSC network. Existing panoramic datasets only provide labels to the visible surface. In this chapter, we present an approach to perform 360-degree semantic scene completion that uses 3D CNN trained on standard synthetic RGBD data and fine-tuned on real RGBD scenes to generate 360-degree results. In our proposed approach, the incomplete voxel grid generated from the input panoramic depth map is partitioned in 8 overlapping views that are individually submitted to our 3D CNN. The resulting prediction is generated from an ensemble of the 8 individual predictions. The result is a complete 3D voxel volume with corresponding semantic labels for occluded surfaces and objects interior. Sample results depict the high level of completion achieved by our approach. Note that the missing and occluded regions in the ground truth of some scenes were completed in their correspondent predicted volumes. In order to show general applications of the proposed pipeline, we also used an in-house dataset called Surrey's spherical stereo images, captured by 2 360-degree cameras in a vertical stereo setup. Stereo capture using commercial 360-degree cameras is one realistic approach, and the capture process is faster than compared to Matterport scanning. However, depth estimation is subject to errors due to occlusions between 2 cameras and correspondence matching errors. To tackle this problem, our solution includes a depth map enhancement procedure that consists of aligning the scene according to the Manhattan principle, applying any edge detector, and using RunSAC to fit a plane over coherent regions with similar colors. The SSC results with the enhanced depth maps were also satisfactory. As in the large-scale dataset, the levels of scene completion and semantic labeling were high. Results demonstrate that the use of a pair of 360-degree images gives an inexpensive alternative to perform panoramic SSC for dynamic scenes where large-scale depth scans are not applicable. Chapter 8 Summary. We introduced the task of 360-degree semantic scene completion. Our method works with high-end sensors or off-the-shelf 360-degree cameras. Segmentation accuracy is close to the limited view solutions. We achieved high levels of completion in occluded regions. This work was published in the 2020 International Conference on Computer Vision Theory and Applications. In collaboration with University of Surrey, our 360-degree EdgeNet model and our depth improvement approach were used in an immersive audiovisual virtual reality system with great results. In this system, our SSC solution was responsible to generate a full representation of scenes captured with a pair of 360-degree cameras. Chapter 9 Conclusion. Regarding the research goals, we achieved our general objective and our specific proposed objectives. The list of contributions is extensive and covers training strategies, network architectures, and CNN building blocks. We achieved 5 publications, 4 high-level conferences, and 1 journal. Even though we believe we have contributed to the evolution of the semantic scene completion field of study towards a more complete understanding of the 3D scene, there is still space for advancing much further. Some of these advances can be achieved by a direct extension of our work, like combining data augmentation and semi-supervision into a single model, extending S3P to explore large-scale real 3D datasets without dense 3D labels, but with 2D labels like Stanford 2D 3D Semantics dataset and Matterport 3D. The resulting model, trained on a semi-supervised fashion with large-scale datasets, could be used to replace EdgeNet as a base model for the 360-degree SSC approach presented in Chapter 8. Okay, that is it. Thank you very much.